Hello, I'm Jurgen Miller, and this is my Python doorbell project. The overall goal of this project was to make a smart doorbell-like device that notifies me about movement at my door. The physical setup is a laptop webcam, and the code takes images with the webcam, processes them, detects changes between frames, and if movement is detected, it notifies me via email and records and uploads a video to Dropbox. The physical setup is my laptop webcam. It's pointed at the doorway from my desk, and I found this was a repeatable location for testing. I could also easily detect my doorway because it's in frame. However, a physical limitation of my setup is that sitting at my desk is in path of the camera. Here's my code logic diagram. First, I take an image, process that new frame, detect changes between this frame and the last frame, and if movement is detected, I send an email and upload a video to Dropbox. Then the whole process is repeated with a new frame. To take images, I use the OpenCV framework. I sampled at a frequency of 10 frames per second, or 10 Hz, which means there's a 1/10 second delay between images. I found that if this frequency was faster, there was not enough change between frames, but if it was slower, I might miss events that happen between the frames. Once these frames are taken, they can be compared each frame to the last. To prepare each frame for detection, they go through this process frame step, which consists of several parts. It is snipped, masked, shrunk, grayscaled, and blurred. Snipping reduces the amount of pixels to process in the frame. It's a rough cut of the detection region. Here, I'm focusing on the door. I then mask them to only keep the pixels in the desired detection region. Here, I'm looking at inside the frame of the doorway, which will catch the door opening or catch someone in the doorway, and the floor below the door, which will detect something inserted under the door, for example, a package delivery. I exclude the gap under the door to ignore someone outside or if light changes in the hallway. I don't want to classify that as movement. I then shrink the image. This reduces the size to make processing faster, and I don't need the high detail of the original image. I then grayscale the image to reduce the pixels to a single dimension, which makes comparison easier. It's very easy to detect changes in brightness in this way. A potential issue here is that a same brightness is not considered change. I then blur the image to reduce high-frequency noise, which could arise from the webcam, from changing light, or slightly moving objects in the frame. I found that a kernel size of 21 was perfect to remove the noise but keep the needed information in the frame. I determined this via testing and viewing blurred frames. If the kernel size was bigger, the movement would be smoothed out over too many pixels and it was difficult to detect it. But if the kernel size was smaller, there would be too much noise in the image that could be detected as change between pixels. After all these steps, the new frame is processed and is ready to be compared to the previous frame, which has already been processed in a previous iteration. To detect movement, I look at each pixel and find the absolute value of pixel brightness change between the two frames. This is the absolute value of frame 1 minus frame 2, and this produces a difference image. This shows the location of differences between the frames. Here you can see that there's a difference where I'm waving my hand, there's a hotspot there, but also a hotspot at the shadow of my hand, because that is moving too. And note that the difference is actually at the front of and behind the actual moving object. That's where the change is occurring. When I'm waving my hand, detection is noted at the bottom of my hand and at the top of my hand. And that's why these seem to have like two lobes in them. If the detection is greater than the threshold, the pixel is considered to have changed significantly. The image brightness is on a scale from 0 to 255, and I found that a threshold of 20 was great. I determined this via testing and viewing the thresholded image to see what movement made it through. If I increase the threshold, pixels could change without setting off the threshold. For example, if it's too high, it wouldn't detect me moving my hand at all. But a smaller threshold could be triggered by background noise, small movement, or small brightness changes across the image. I found in testing that my laptop webcam adjusts the brightness of the image when a face is detected in the frame. And if my threshold was not high enough, it would be triggered by this brightness change across the image, even though nothing had entered the detection region. In addition, too low of a threshold can be triggered by a shadow. Here you can see my shadows being picked up with a low threshold, and even if my hand was out of frame, this would be classified as movement, which I did not desire. If enough pixels change significantly, movement has been detected. The threshold for pixel count was tested by moving objects in the frame and finding what worked. A helpful tool was printing out how many pixels changed and corresponding that to the size of the movement that was happening in the image. My desired threshold ended up being 50 pixels. And I found this was perfect, so that if I move my hand in the frame, it sets it off, but just wiggling my fingers around in place does not. If movement is detected, I'm notified via email. This sends the two compared frames to my email, and I made the design decision that these images are not recorded locally, they're only sent in the email. I figured it's a useful notification, but it's not a lot of information worth storing for later. On the other hand, the video is a very important information for the user. I record a video, save it to file, and upload a video to Dropbox. I used a unique name using the timestamp with a 1-second resolution to name the videos so that none would ever collide with each other. And they upload to a designated folder on Dropbox so that they'll all be available. I accomplished this using Andrea Fabrizi's Dropbox uploader script from GitHub. When this whole process has completed, we loop back to the beginning and to compare a new frame. When running the actual program, selected stages of this pipeline are visualized. Here you can see that the original frame is shown, and then the mask of that frame, which occurs during the processing step. Then the final processed frame is shown, and then below it, I detect the movement for the pixel difference between this frame and the last frame, and you can see certain hotspots. Then I threshold that and have that thresholded pixel difference as one of the last steps of detecting movement. Here you can see some white spots there, and if there were enough pixels changed to count as a detection. You can see in the bottom at the output that a detection message printed with the timestamp. And when detection occurs, a video is recorded. The original frame is replaced by the video when recording, and the rest of the detection pipeline freezes on the frame that triggered it. Here I'll show a real-time demonstration. Here it'll initialize my webcam, and I'll try to be still so that it doesn't think I'm moving. Oh, I already moved too much. So here, it's recording a video of me because it detected movement between the frames. And once it's done, I asked it for a 10-second video. It'll upload that video to Dropbox and email me things. And here I moved again, so I triggered this again. Now I'll show that in my email, I've received an image, 2 images, the timestamp, and I can see the images that set off the movement. So here, me moving around like that was enough to set it up. And on Dropbox, in my Python Doorbell folder, I have a new video that shows what happened after that movement was detected. Here's a demonstration showing that when it's actually set up to look at my room, the doorbell ignores me because I'm not in the doorway. But when my roommate Colby enters the doorway, he will set off the detection. So here he enters the room, and now it's recording a video. And thus afterwards, I get notified via email. I get a picture of my door opening with a timestamp. And in Dropbox, I can go and see, and I get a video of Colby opening up my door here. Even if the door was already open, and this will introduce a lot of noise to the image, you can see. Colby's blending in with that noise right now. But when he actually comes into view, there's enough movement to be detected. And once again, I'll receive an image of him walking in and a video of shaking his hand here. Next up, even if my door is closed, but then someone slides something under my door here, detection is set off. So this is useful for finding out if I have a package delivered. I would be notified of this and receive a video of it being delivered. My pipeline is similar to that shown in lecture videos, but has some differences. First, I snipped the image to reduce the unneeded pixels throughout the pipeline. This made processing faster in general. I also displaced stages of the pipeline, which was very useful for debugging and also presentation purposes to show how it works. I added more exact timing. I took frames with timing loops to ensure accurate and steady frequency, and this meant that the frames were taken independent of processing time, as long as the processing time is faster than the delay between the frames. The video is also taken at an accurate desired FPS, and comes out to be an accurate desired length. My code is also made to be modular. The different functionalities are split into self-contained methods, which means they could be easily changed later, and also they were easily individually tested and then brought together. I also limited hard-coded constants. If they were needed, they only appeared once, for example, the thresholds I've been talking about, and the code can easily adapt to changes in these constants. This project could be improved in terms of hardware and software. For hardware, the camera could be mounted in a better position. It could be mounted somewhere to get an unobstructed view of the desired area, and it could be mounted outside of my room or even be looking through a window to capture a desired region. I could increase the field of view with the camera with a lens, which would provide more information. And in terms of software, object tracking could be implemented for movement detection instead of brightness. This would mean that the algorithm would not be fooled by brightness matching the background. In my example, if you walked in with something that is just as bright as my door, you might be able to not get detected. And I could always be recording video to a circular buffer, and this would mean that when movement is detected, I already have video of the recent past. This would mean that the end video will span from before the movement to after the event ends. This could record important context that happens outside of the detection region before movement is detected. For example, if I get a delivery, I might get a video that includes seeing that before it was delivered, it was dropped on the street. I only get that if I'm recording video before the detection happens, but then include that in the video. Overall, the goal of this project was achieved, and I improved my OpenCV skills, and it was a fun project to complete. Thank you.